name and tell us about your project.
Okay, hello, my name is Clinton Davison, and in 1923 to 1927, Lester Germer and I performed our experiment that we now call the Davison-Germer experiment. We designed a vacuum-type apparatus for the purpose of measuring the energies of electrons scattered from a metal surface. Electrons from a heated filament were accelerated by a certain voltage and allowed to strike the surface of nickel metal. And this experiment confirmed the hypothesis of Louis de Broglie.
What were you guys trying to do or find?
Yeah, so like I mentioned, there is a hypothesis advanced by Louis de Broglie in 1924 that was related to wave-particle duality, which was eventually a breakthrough in quantum mechanics. And our main goal was to confirm this hypothesis, or one of our main goals. And according to de Broglie, for all matter and for radiation alike, the energy of the particle was related to the frequency of its associated wave by Planck's relation, Planck's number.
Where did the project or experiment occur?
So we did the experiment at the Western Electric Engineering Department, which is now known in the 21st century as Nokia Bell Labs, and it is located in New York City, New York.
What other significant events were happening around the world at that time?
So a couple things. In January 1st of 1923, the Model T Ford came out with the first affordable car that they had. And on January 1st of 1927, Babe Ruth became the first player to hit 60 home runs in a season. And another big thing, on May 20th, 1926, the Air Commerce Act was passed, providing aid and assistance to the airline industry, just to name a couple things.
Cool. Luke,
Liza,
can I scroll down?
Can you see
Can you
this?
scroll down?
Oh, it's right up here.
Oh, I see it. Sorry. Who else was involved in the project?
So an important contribution to the experiment was made by Walter Elasser in Göttingen, Germany during the 1920s. And he remarked that the wave-like nature of the matter might be investigated by electron scattering experiments on crystalline solids. And this suggestion of Elasser was then communicated to his colleague, Max Born, who was a physicist in England at the time. And when our experiment was first performed, the results of the experiment were explained by Elasser's proposition.
What was your role in the project?
So in 1921 or so, I began to study electron bombardment and secondary electron emissions. And like I mentioned, Max Born, who helped us, he gave a lecture that used diffraction curves from my 1923 research, using the data as confirmation of the de Broglie hypothesis. I learned that in prior years, other scientists had attempted similar experiments, but were unable to generate low enough vacuums or detect the low-intensity beams needed. So I returned to the United States, and I made modifications to the tube design and detector mounting. A couple things I added as azimuth and coalitude. Following experiments generated a strong signal peak at 65 volts and an angle of 45 degrees. And I published a note to the Nature magazine titled "The Scattering of Electrons by a Single Crystal of Nickel." So although electron energy diffraction does not follow the Bragg law, it did confirm de Broglie's equation. And to sum it all up, I was just one of the lead scientists in the experiment.
What impact did your project have on the physics community?
So our experiment really demonstrated the wave nature of the electrons, confirming the earlier hypothesis of de Broglie, putting wave-particle duality on a firm experimental footing. It represented a major step forward in the development of quantum mechanics, and this was the first application to particle waves. My partner Germer and I had just proven one of the underlying principles of quantum mechanics.
Cool. Where did you get the inspiration to conduct such an experiment?
That's actually the wrong question. Crap. If I've received any awards.
Did you receive any awards for your experiment?
Yes, I actually received the Nobel Prize for Physics in 1937 for experimental discovery of the interference phenomena arising when crystals are exposed to electronic beams.
Cool. Well, thank you for your time.
Yes, no problem. Thank you.